Hello. Hackers and hackers, welcome to the next talk that tries to make a pragmatic shift in Bluetooth security. Thierry Zoller of Enrons and Kevin Finisterre, who cannot be here because of reason beyond his control today, will show a complete pragmatic shift in Bluetooth security, why your company is at risk, why your security measures will not work out like you maybe thought, and what you can do on all levels of Bluetooth, from the lowest level to the application level. He will show like how to get a root shell via Bluetooth. Yeah, I've seen this talk already on HackLU. I can just wish you a lot of fun. Please, warm welcome, Thierry Zoller.
So, okay, Microsoft working. So let's start off. Yeah, basically the recommendation: turn off your Bluetooth, not because that's uncool, but simply because Kevin said so. That's Kevin. And basically there will be code released that may lead to the compromise of your box if you enable Bluetooth. So just turn it off as a recommendation. If you don't, not my problem. The goal of this talk. The goal of this talk is not to build myths or to show off and not to show how. So I'm trying to show you how exactly I'm doing things, more the full disclosure nature. I'm limited in time, so sometimes I will scratch the surface. I'm free for questions and comments afterwards, so feel free to ask. The goal, of course, is raise a bit of awareness, make risk more transparent, and show cool stuff. So, what are we talking about? So basically you have an introduction. I'm sorry you have to do this, because else it doesn't make really sense. You can't really estimate the risk or see how it works without it. Extending the range, you all know it. And implementation issues and protocol specification issues. Basically that picture, quite funny, because I thought that's a good representation of the Department of Homeland Security, that threat level, the terrorist level, that's basically always at this stage, so please panic. Okay. So a few tidbits about Bluetooth. Operates on the non-regulated ESM band, 2.4 GHz, in general 79 channels, except who they thought is France, Spain, because it wasn't regulated there, and the military use parts of the spectrum. So in France it has, like, I believe 23 channels. It does frequency hopping, which is, let's call it a security through obscurity layer, because that's what prevents general people from auditing or really looking deep into the protocol stack. It is a complete framework with profiles and layers of protocols. It's not like Wi-Fi. It's a complete framework, so it has layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. And it's completely defined. It's with mandatory profiles, so it's big, really, really big. The specification 1.2 has 1,200 pages. It's a nice framework, it's very well thought, but the specification is a mess. And it's not really a wonder that actually those who implement these things kind of do things differently. What's funny about this is that in specification 1.2, the new thing about the specification was, well, we will introduce specific meanings for shall, must not, must, which normally is a requirement for the first version, for instance, but, well, they thought, let's do it for 1.2. That basically explains also why some implementations are messed up. Interesting also, the 1 billionth Bluetooth device was sold in November this year. That's kind of a huge number. And always to keep in mind, the goal for Bluetooth was least cost cable replacement, low power usage. So the goal wasn't security, the goal was actually to have little gimmicks with Bluetooth that cost like $5 to produce, and that's it. So the security was pretty much produced around that ultimate goal of low power usage and least cost cable replacement. So the foundation, the protocol stack, we have the different layers, some implemented in hardware, some in software. We have the baseband, which is basically responsible for, which is the physical layer, which does the hopping, which does error correction. Then you have the LMP, which does security and quality of service. Then we have something that's called HCI, and that's basically an interface that you can reach as a user to communicate with the layers below. So if you do an HC tool scan, that's actually the implementation here that goes down towards the hardware layer. Yeah, then we have the L2 cap. L2 cap is basically a multiplexer, demultiplexer for the protocols above, as you see. Then we have RFCOM, which is a serial emulation. And basically we have everything you know above, and here's layer 7. So, Red Fang, Oli Whitehouse, you all know it probably, brute forces devices which are in non-discoverable mode, so they can't normally be discovered. His implementation does like 23 MAC addresses a minute. He made a parallel version, so you can put up to, I believe, 127 Bluetooth dongles with hubs. Of course, you look like a tree afterwards, but you can optimize the brute forcing pretty much. It's not that reliable because sometimes it misses. That's very well known. It uses a read remote name, which, to my belief, acts as the LMP layer. Not so known is actually that you can use the layer above, the L2 ping. You can ping devices which are in non-discoverable mode. I've not seen any implementation of this, but to my belief it should be a bit faster than this method here. We'll see another method to find a big chunk of the MAC address passively. That's going to be one of the main findings. So a typical Bluetooth scenario, typical between Gänsefüßchen. Actually, the baseband sends inquiries and the device sends an inquiry response if it's in discoverable mode. So that's how you find devices. If you do an HC tool inc, it will actually send inquiry and inquiry packages. We will see how this works exactly afterwards. It's completely different than wireless, than Wi-Fi. Sorry. Yeah. Then the Bluetooth access point says, well, I'm here, I can be reached at these frequencies, so the handshake, what is called the frequency hopping sequence. Actually, like I said before, they hop around 1,600 times per second at different channels. So actually the paging is a synchronization between the master and the slave, which tells it, hey, in X microseconds, I will be on this channel listening for a packet, and then on this, and then on this. And so they agree to hop at the very same frequency. What's interesting is that a piconet, which has 7 active slaves and 1 master, actually hops at the very same frequency altogether. We'll see that afterwards too. So the link is established using the LMP layer. It may discover profiles over SDP. It's a very basic Bluetooth scenario. Then it goes up to the RFCOM and actually establishes a connection towards a profile defined above. So the inquiry, the first contact. How do the devices find each other? One could say, let's say all Bluetooth devices will meet at a specific channel, let's say channel 78. But what happens if somebody puts a chicken in the microwave and that channel is jammed they couldn't meet. So what was the solution was that during the inquiry stage, every Bluetooth device hops at a specific frequency. They always hop exactly at the same frequency. And that's why you can find devices that are in discoverable mode, because they hop at the same frequency. And you're trying to listen at this frequency, to send packets at these frequencies and find them. So during inquiry stage, you also pass parameters like this is my MAC address and this is my clock offset. The paging, frequency hopping synchronization. Slaves always sync to the master. Actually, at initialization level, the slaves hops one channel a second, very slowly, but the master just goes over it 3,200 times a second. Then the second step in paging is both have synchronized and hop at 1,600 times a second. So what's important is that the Piconet agrees to sequence based on parts of the Bluetooth address, and that's a BD address, looks like a MAC address, has 48 bits, and the clock offset of the master. Every Bluetooth device has a clock. Every Bluetooth device has a pseudo number, random number generator. That's kind of cool, like we will see afterwards. And frequency hopping is the reason you cannot easily sniff Bluetooth traffic, so you can't put your device in monitoring mode and hop, you'll find you will sniff everything. It doesn't work out because you don't know at what frequency these devices actually communicate and at what frequency to listen at. So you could, of course, use a spectral analyzer and reconstruct afterwards, but you have to implement the whole Bluetooth stack, the baseband, the R radio frequency, and pretty much of a challenge, so good luck. Bluetooth profiles, I'll pass over it pretty fast, represent a group of defines of mandatory options, so they are mandatory. That's one part of the framework that's pretty well done. Actually, to have compatibility, you can discover the profiles a device offers. So you can ask it, what service do you have to offer to me, and we'll give you a list, and we'll also give you a list to how to connect to it. So you will see that here's OBEX push profile. We'll see, of course, the baseband. That's mandatory. So we have the L2 cap layer. That's an output of SDP browse tool from the BlueStack. L2 cap layer, the RFCOM layer, and the OBEX. Different Bluetooth modes, discoverable modes, sends inquiry responses to all inquiries, limited discoverable, well, depends on the implementation, visible for a certain amount of time. There's, Ericsson, yeah, okay. There's also implementation bugs. At this level, Sony Ericsson implemented what is limited discoverable. They are just discoverable for 2 minutes. So you activate it, says discoverable for 2 minutes, and then afterwards, normally it's no longer discoverable, except you ping it. If you ping it, it will stay discoverable forever. And the funny thing is, when it's discoverable, it's attackable. And since this has the basic attacks, blue bug, and whatever the name for the other one was, the AT commands and the OBEX stuff. Non-discoverable, it never answers to an inquiry scan, and that's, of course, in theory. Then we have the pairing modes, non-pairable mode, reject every pairing request with LMP not accepted. There's also implementation bugs on this layer, because Plantronics managed to really fuck that up. That's a headset like this. It has a nice button to it, which makes it in pairable mode. Then the light starts blinking and you see, oh, I can pair now. The problem is the button is just cosmetic because it's always in pairable mode. So, okay. So that's another implementation issue. They got it wrong. Pairable mode will pair upon request. Okay. So, extending the range. That's from Kevin. Kevin tried to measure the distance he can get with I think that's an 80 dBm Yagi. Actually, Kevin was here, and his phone was there. And he put the phone on the bank with a note saying, here, hey, this phone is here for a reason. Please don't take it away. And while he was here, pinging the device, he lost the connection. And then he saw an old man walking by. So he took the Yagi and adjusted it to the man, and it responded to pings. So, so actually, he got it back from the man afterwards. So you can not only optimize for distance, but also for penetration. That's a thing I built up. It's actually based on a toy. That part is a toy, that part is Yagi. Well, I have it here, actually. Looks quite funny, and was the reason I couldn't get here by plane. So I drove like 7 hours just because of this, anyways. So the parabola is metallized. I used zinc spray. Well, it's definitely not the best method to actually have a clean surface to reflect the stuff, but it worked out pretty well. Actually, I just made it as a joke to see if it works, and it actually worked because, yeah, I had the occasion to test it at a bank, and the problem was not discovering devices in the bank, but I found devices in the bank behind that bank. So I had to go around the bank to actually exclude the other devices. Well, it has a USB cable over here. You have what's that called? A zoom, yeah. You have a 10x zoom here, which can compensate for eye vision problems. The only thing I'd like to add is like a laser pointer, because at these distances, every millimeter actually counts. So that's Kevin implementation of the parabola idea. But he went a bit further. He actually used an NSLU, which is a Linksys storage device, which I thought I had here, but I at home don't have. It runs Linux, so he installed his own attack tool. It can attack automatically. It's completely autonomous. He can actually have it at some place, and it will collect, scan, and if he wants also attack every device it finds, it saves the results for later usage. What's funny is that at the beginning this part was solitary, and he wanted to actually hide it within a rock, so you could plant a rock somewhere or whatever, a Coca-Cola bottle, and that bottle will attack and collect all your stuff. So perimeter watch, that's again something from Kevin, which by the way really did a lot for this talk. So I'm not the only one doing this. I'm presenting it, but a lot of work was done by Kevin. So it's a Perl script by Kevin Finisterre. It searches for Bluetooth devices. Once it finds some device, it takes a 360-degree picture and saves down the GPS coordinates. So you can download at his website, which is digitalmunition.com. So let's go to the implementation bugs. Bypassing security. That's that's Belgium. So we have remotely controlling workstations, car whisperer, NG, owning internal networks, link theft, abuse, overflows. So did you know the Bluetooth pin is actually a Bluetooth passkey? It isn't not necessarily a digit, but actually nobody really implemented the specification, because you, instead of just entering this, you could enter this. And it's kind of awesome, because that's like inventing NTLM and just implementing it with digits, which is kind of absurd, because you can increment very, very fast to all digits, but you can't increment through all the UTF-8 space pretty fast. If the vendors would have implemented this, my BT-crack tool would take a long time, but they didn't. The reason why is probably because not every input device has characters, But come on, I mean, you write SMS with your mobile phone. Why don't you implement this? Why do you take tickets? It doesn't really make sense. And the specification, it's there. It says use it, but they really don't. So, Cowrisprov by Matt and Herford, it's actually, you know it well. You can listen and record conversations. You can eavesdrop on headsets, hand-free kits, but it works also against workstations. And that's kind of interesting. Actually, Whitcomb, there's Windows. Below 4.01 or 1500, there was no pin code, and you could actually listen to the conversation, and also, like with the car, you could inject audio. For this to work, you have just to remove the class ID check or change the class ID check within the CV scanner script for it to also try to connect to laptops. Kevin, in fact, also did a real-time patch for it. And now you can take your mic and actually talk in real time instead of playing a pre-recorded WAV file. You can download that too on digitalmunition.com. So, hit attack, owning Bluetooth VNC style. That's by Colin Mulliner, who is here today and who allowed me to publish this. That's kind of O-Day, and you can get it here. That's one reason I said, please disable your Bluetooth. HID is actually a human interface device. It requires two PSM endpoints to act as a server. There are two implementations. The keyboard connects to the HID server, or the HID server connects to the keyboard. The funny thing is, they don't necessarily authenticate these connections. So you actually below Blue's 2.25, and you had the hit daemon running, you could connect to it and actually type at the keyword just like you were in front of the PC and actually control it remotely. Of course, you don't necessarily see the PC, but you can inject on pretty much everything. You can open a shell and inject commands or whatever. So yeah, thanks Colin for letting me releasing this. It's actually a bit more complicated than this. Within it attack, you'll get all the info and stuff to do this. So that's quite interesting because I haven't really checked on Windows. Neither has Colin, as far as I know. So maybe there are Toshiba, Whitcomb, or whatever implementations that are also vulnerable. So try it out. So to the demo, trying to show you how to own internal networks over Bluetooth. Actually, OS X 10.3 was vulnerable. OS X 10.4 was vulnerable, the vanilla release. Windows was vulnerable, the Whitcomb implementation, the Toshiba implementation, the Blue Soil implementation, and maybe others. And the Pocket PC was vulnerable to the same attack. Well, Kevin told them that they had this issue in an OBEX FTP server, that it's non-authenticated, so everybody can connect to it as soon as you plug in a Bluetooth device. They had kind of the OS 10.4 master CD just ready to be pressed or burned down, so to be shipped off. So they couldn't fix it. So they fixed it in 10.3.9 before fixing it in 10.4, leaving those vulnerable for over a month to a rather very simplistic, as you will see, very simplistic and very frightening bug. What's important is, of course, that's patched, and that's patched for like a long time. That's patched for over a year. So the reason why we'll show this demo is not because the actual bug is that interesting, but because pity to raise awareness. You can be owned over Bluetooth. It's not only for toys. Your workstation can be hijacked. Pretty everything that works over Bluetooth. And of course, to ask the question why some operation system vendors don't test their stuff, because there's things like SDL, Secure Development Lifecycle, and I don't think that a directory traversal exploit in an FTP server is that difficult to find. The cause practically is that the usual OBEX FTP implementations, the tools you run on your box, actually filtered out these commands. So in order to find this, Kevin had to just patch it to actually allow ... So, and that's everything, except of course BTFTP, which is in the blue CVS version, which doesn't check for this. The combination of this exploit is pretty interesting too. So there's an OBEX FTP server directory traversal. That's Kevin stuff. Kevin then plants a malicious input manager, launches a local remote exploit, binds etc. TTYs to RFCOM, and we get a shell. What's interesting is that this is not only possible. It was not only possible on Mac, but it was possible on Windows, Pocket PC, and pretty everything that has a Toshiba Broadcom, which is now Whitcomb, stack. Probably most others too. There are not much left. I don't know any there. Bluesoil is still there. I don't know about Bluesoil. But we choose a Mac just to show that Macs are not invulnerable, and basically you can own internal networks over Bluetooth. So over to the demo. Can you please swap over to this PC? Oh. Yeah, rude. It's a box I set up in 2 days. I don't give a fuck. You can own it. Oh, jeez. So I'll just plug in the Bluetooth devices. Of course, if the Mac comes with a Bluetooth device built in, it works too. So, yep, seems to work. Oh, Jesus, I don't see anything on the screen. So I activated actually the device. I will run the demo and show you the script afterwards. How is this done? It's quite interesting to see. I just launch it and hope that it works. Because sometimes it just core dumps when you connect to it. When you launch too many RFCOM connections to a single port, it tends to core dump. So here's the directory traversal going on. He plants the input manager, he plants the local root exploit. Interesting to know is that it uses the Bluetooth address name, the Bluetooth name, to actually find the user directory name, which is Terrizol in this case. So
I am a Mac. I am a PC. We both suck.
So now it's going to reboot. That's on 10.3.9. On 10.4, you don't see anything. It won't reboot. You have a shell immediately. What's interesting is that due to the input manager, which Apple calls method swizzling, which is actually like, if you know the Windows world, like app init, which you can use to inject the DLL into a process. It's actually similar, just that Apple chose to implement it globally and not only based on a single process. So if you have an input manager, and as soon as any binary is launched, the input manager launches too. And that's practically the auto-start vector Kevin used. And that's basically why we disconnect and then we reconnect. Because when we disconnect, the input manager is planted, the OBEX server closes, and when we reconnect, the OBEX server launches and launches the input manager, which launches the local root exploit, which actually changes, etc., TTYs. So without Apple implementing that global input manager thing, that input manager feature, that wouldn't work out. So let's see, we should have a shell here. If it came back, I don't know. Well, I'll just show you. Oops. Ah, jeez. So that's basically how it feels. That's here it gets my home dir. It extracts Cherry Zoller from the input. There you see it. It's a plain, obvious directory traversal. He makes directories, he traverses the directories, and this is unauthenticated. So anybody could connect to your OBEX server and just traverse your whole directory system. And I'm sorry, but every 13-year-old knows that when he's writing an FTP server, he better filters out this stuff. I mean, come on, you can't be serious, but they were. So that's the local root exploit he puts there. And that's actually the phrase here. Yeah. Okay, I think it should be back up. So interesting to note also is that now we don't need to log in because Apple chose to have the RFCOM port 3, which is there for syncing your PDA, to have it open even before you log in. And as Kevin bound it to port 3, we can now connect to it even without that user logged in. So that MAC address is obviously spoofed or changed. So there we have. So that's hello. Oh, there we are. So what user are we? We are user Bluetooth. We'll see this in a minute. Actually, what I use here is AT shell, which comes with Blue Diving, which is a nice auditing package for Bluetooth. It uses code which actually was written for Blue Chase, which was a project from the Chaos Computer Club in 2003, I believe. I used that code to launch a shell instead of just using RFCOM and using Minicom. Oops, that was my microphone. Using Minicom to connect to the port. So I'll just launch the shell. I'll launch the local root exploit, and we should be root. That's it. Now we can scan for other devices, compromise other devices. That PC may be within a company or whatever. It may be a Windows PC or something along these lines. Important is, if you update your machine, it's patched. Kevin waited over a year until he published the stuff, so I think that's, he made public the stuff, so I think that's pretty reasonable enough. Oh, another thing. Oops. Well, it's kind of slow, but it works. Well, anyways. I think I pretty much showed the point. Getting my microphone over here. Oh, cool. It worked. So there are the link keys for these devices. We have, that's actually another device. It's not that beef, that was another USB stick. These are the devices that the Macintosh was authenticated to. Now, if we copy these link keys towards our Linux box and drop it in, etc. Bluetooth keys, we can now connect to this device and pretend to be the Mac, and we will be authenticated towards this device. So we can actually use the services. That's about stealing the link key, which I will show afterwards. Also, the concept behind this. So, can we switch to this PC again? Okay, thanks. So, what was funny was that I had this Mac running on 10.3.9. It was patched. It was patched against the local root exploit he used in his previous versions. So he just said, "Oh, wait, I'll just send you another one." And it's actually, yeah, that's important. Watch out for January, because he will make a month of the Apple bucks, and that will be like an O-day route a day. So that's scary. That's Calvin too. That was his girlfriend. Windows Whitcomb, buffer overflows. So we have remote code execution also in these drivers. There's plenty of stuff. There are basic implementation issues, the // there are buffer overflows, there are format string, there's pretty much anything. This special exploit only works 1 out of 4 times, because the shellcode is Unicode, that's not the problem, but actually the address is based upon the BD address, and that's somehow is mixed with other stuff, and that changes. So actually the exploit is successful just 1 out of 4 times, but when it works, it works. So actually versions known to us are these. There might be others. They are all patched. The problem with this is pretty obvious. Who in this room knows, and just wave your hand, who in this room knows what version of stack he has installed on a Windows machine, if you use Windows? What stack version you have installed? If you know, wave your hands. You see, that's the problem. Because, and it isn't obvious for me too, I had to look like 5 minutes to find the version number, because it's in some registry key, and whatever, it won't update with Windows Update. Most people believe, well, I have a Bluetooth stack, so, well, it will be updated with Microsoft. No, actually, most vendors choose not to go with Microsoft stack this time. And it's strange that there wasn't any public bug within that stack, but there was plenty of bugs within third-party stacks. So, that's important. If you update your machine, it won't update the third-party stack. That may be obvious, but it's not obvious for the general user. You have to actually go to the site and download the patch to actually have it running. So I guess there may be a lot of persons within this room to actually have a vulnerable version. That said, Whitcomb was bought by Broadcom, and it's pretty darn complicated to have your old Whitcomb stack updated. So actually there might be lots of people that run vulnerable code and they don't know it. But that's nothing new. So, protocol issues. That's, I don't know if you recall him. It's Iraqi information minister. So why the pin is not that important? The problem with unikeys, how to find non-discoverable devices, random number generators that may be from hell, link keys, reconstructing them, abusing them, reinforce pairing corruption. So, why the pin is not that useful? Actually, this is the authentication logic implemented in the 1.2 protocol. The pin is not really that useful, the link key is. So, as an attacker is after your link key, it's not after your pin. Your pin actually, if it's not hard-coded, it needs user interaction on the other side, and the user will, of course, see that you want to connect and ask for a pin. So that's pretty obvious. The link key is, basically, here's why. The authentication starts. So the link key is authenticated already. Yes, well, whoop, authentication, okay, but that's obvious. Is a link key available? Yes, it will authenticate a link key. That's basically Diffie-Hellman like they do in the pairing. If that's okay, you authenticate it. The pairing, the moment you enter your PIN, is actually here. So if it's not authenticated, if you don't have a link key or the wrong link key, then you will enter your PIN. So that means if we have the link key, we can actually go around the pairing process, which implicates that you actually manually enter a user PIN, a Bluetooth passkey, as we call it now. So the link key is enough to authenticate. Important also, the encryption that uses the AO algorithm can be calculated from the link key. So as soon as you have the link key, you can decrypt the traffic, and that's also very important. Also not so obvious is if we have the link key, we might not only connect to the slave pretending to be the master, but we can also pretend to be the slave connecting to the master with the same link key, and it will work. Unique keys. Unique keys are generated by the device. Actually, I have not seen them. Actually, they are for very, very small devices. I hope it's not used that much. They are based on a pseudo-random number generator that may come from hell, as we see afterwards. It's permanently saved and cannot be changed. The problem is A has a unique key. It authenticates to B. Afterwards, A authenticates to C. And because the unique key is the same, B may now decrypt the traffic. That's also why the SIG clearly does not recommend its use, and it's within the specification. It's just that it's not so obvious, so I mentioned it. How to find non-discoverable devices passively, and that's very important too. We knew Red Fang, we know now that L2 ping works. Our target address is a 48-bit address. I think that's Nokia. Actually, Red Fang has to brute force through all the different BD addresses, and actually waits for someone to answer. To further reduce the space, Joshua found a really slick way. Here's what he does. We sniff on a preset channel and wait for devices to hop by, capture the Bluetooth preamble, extract the channel access code, which is based on 24 bits of the BD address, and recalculate the BD address, so we have this part. Then we extract the error correction field in the baseband header, which is basically CRC, it's a 10-bit field, and we have this part. Now, step 3 is assume the first bit 0. That's easy. And what is left is 8-bit. So we just have to brute force 8-bit, and that's pretty easy and pretty fast and pretty reliable, because if we miss a device, no problem, we just start over and we'll find it. That does only work with the sniffer, and we see that's the crutch here, because currently there's just commercial versions, and they are not cheap. You might find them on eBay, but the goal here is, for everybody of us, should be actually to make this technology to sniff available to everybody, and then we see Bluetooth will pretty much crumble down, because what saved Bluetooth was that in order to really dig down in the foundation of the protocol, you need a sniffer. You need to know the hopping sequence, you need to follow it. And it's pretty much security through obscurity, not because of the implementation, not because they didn't publish the ciphers or they did reinvent the wheel, but simply because to actually really audit a device, you have to follow the hopping sequence, and you need to buy a device like this, which is a BPA 105, which sold around $10,000. You may find it on eBay for $1,000 or less. And that's pretty much, if we as a community find a way to actually hop these sequence, to actually find the frequency hoppings. To actually find the frequency hopping sequence. With a software implementation or similar that works out of the box, this thing will crumble down pretty fast, to my belief. So we brute force the 8 millibigs. So the random number generators from hell. Specification is not very clear about what to achieve or how to achieve it. Actually, the specification is 1,200 pages, and the thing important about ciphers, as we all know it, is pretty much the quality of the pseudo-random number generator. Of course, you can enhance it by hashing and so forth, but you should pay attention to actually get random values. And the part specifying the random number generator is actually this big. And it starts with an introduction, it's like this, and it reads each device has a pseudo-number generator, pseudo-random number generators are used many purposes within the security functions, for instance, for the challenge response scheme, for generating authentication and encryption keys, etc. In other words, we read this, it's really, really important, so don't mess it up. And then it reads, within the specification, the requirement placed on the random number generators used are non-repeating and randomly generated. Okay, what does that mean? For example, a non-repeating value could be the output of a counter, that is unlikely to repeat during the lifetime of the authentication key, comma, or a date and timestamp. So, we know that there's a clock inside each device. So, where do they take the seed from? Remember that we can't get the clock offset with a simple non-authenticated inquiry. What if someone reads the specification like I did and follows the specification? Actually, I didn't have time to actually measure the quality of the output, but I guess some implementation should be really fucked up, because what is a specification worth if it goes like, oh, random number generator, use randomize, generate random numbers, it's fine. No, it's not. So they don't trust it themselves, obviously. The reason for using the output of and not directly choosing a random number as the key is to avoid possible problems with degraded randomness due to a poor implementation of the random number generator. So they pipe it to E2 mode 2. But actually it doesn't it helps, but come on, it should be random. So introducing BT-Crack, it was first presented at hack.lu. It's actually released right now, so you can find it on the website, you can download it now. It cracks the PIN and the link key. It requires the values from a pairing sniff. For convenience, you may import CVS data from your capture. Interesting thing, if you download it now, there's a hidden message inside the zip. The first person to find it will get the source code. So just do as the message indicates if you have wireless. I don't think many have, but if you have, download it and do as the message says, and I'll give you the source code afterwards. Obviously, we'll release a Linux port with the source code afterwards, but you'll get it now. So the history. Ollie Whitehouse, 2003, he presented the weakness of the pairing process and how it may be used to crack the PIN. He didn't implement it, he presented it. Shake and Rule actually implemented and optimized the attack. They found ways also to reinitiate pairing, which is the key point, because to crack the key, you have to sniff on the pairing process. And the pairing process actually just happens once in a while. But if you can actually reinitiate the pairing, you can capture it live. So you say that you can actually the implications of the attack are a lot bigger if you have a way to reinitiate the pairing. So it felt quite awkward to actually write my name there. There was tremendous help from somebody that will recognize himself. It's a Windows 32 implementation, first public release. Whoops. So just to give you a few numbers, version 03 did 22,000 keys per second, 05 did 47,000 keys per second. That's actually just because I implemented threading, and because it's dual core. And then thanks to Eric Sesterhan, we actually optimized the whole logic for caching. He cleaned up the mess, he used static functs, he removed the junk, and he compiled with ACC, which gave this, which is quite the difference. You see that. Clean coding does help. So we have a 4-digit PIN pretty much in real time. 4-digit PIN in, well, it's not real time, but pretty close. So Windows XP recommends 8 digits. And well, I haven't measured here, but it's below. It's around 11 minutes. So unless you change the PIN. Okay, can you come after the talk? So I'll give you. So somebody reads the license agreement. So just come after the talk, come see me. You'll get. I'll either give it immediately or send it over email. Where was I? Yeah, Windows recommends 8-digit pins. So unless you change the key, the link key every 10 minutes, you're not really secure. Oops. I think Apple, what does Apple? Also 8. 6, 8, something around the line, but it doesn't help really because it's digits only and they don't use UTF-8, so it doesn't really matter. It's pretty much broken. That's the logic of the pairing process. You generate a random number. Yeah, I'll go through it pretty fast. In the middle is actually the value that we can sniff. And if you go through all the logic, you'll see that everything, the thing that is left out is actually the pin. The pin is the shared secret between the device A and the device B. So, yeah, obviously pin length, we can get the pin length, because if we have the pin, we have the pin length, obviously. So there's just one thing, and it has a very low entropy. So here's the logic of shakedown rule. And here's pseudocode from Thomas Rybicki, published in Hacking 9 in 2005. And it pretty much shows everything. You calculate the hypothesis for k init, which is here. You decode L key round and L key round B, which is here. You calculate the hypothesis for ka, which is here. You calculate sres out of our round, which is here, and you compare it. If sres is sres, we have the key. If not, we'll start over and we'll increment the pin. And we go over and over again until sres A equals sres. So let's demo this, and I hope that thing won't crash, because the driver is pretty fucked up, and if you connect the USB cable and you retract it and you reconnect, it blue screens. That's actually one new feature of the new version. Let's just to mention it. That's software that costs over $10,000. One feature of the new version is the driver is more stable. So let's see if this works out. That's quite a benchmark now, because all these interferences. We'll see if it works out. I will actually synchronize to the master, which is this device. It has a few options to synchronize. Synchronizing in Bluetooth terms is getting the frequency right, knowing where to hop next. So we'll start and see if it works out. Here at the bottom we see BPA waiting for frequency hopping sequence. Oh, there it is. It's synchronized. So now I'll try to pair up with that vulnerable version here. So, oh, sorry, I forgot. Somebody give me a pin. Just a pin.
2342.
I'm sorry, I did mess up. So let's start. So 2342. Okay. No, didn't work. Try it again. So you see it's very reliable. Oh, come on. I don't have time. Okay, now it should work out. Yep, it's synchronized. We connect. $23.42. Yep, $23.42. Yep, should have worked. So we have lots of baseband errors. but never mind, that's normal for Bluetooth. No, actually, because there is interferences. So within the handshake, there's also an algorithm for error correction, which says, whenever you don't get the packet, hop at this sequence next, I will retransmit it there. So it's really complex. It's not easy stuff. So the LMP layer, which is basically for, let's see if we captured everything here, which is for security and handshaking, will export it to a CVS file, which we may later import into BTCrack. So there it is. We load up the CSV file. There it is. Oh, Jesus. We missed something. A reason ruin. Do we have time to replay? Okay. So let's resynchronize. Very reliable. We have to actually remove the old pairing because it won't ask me for new pairing credentials if it's actually already authenticated. So I'll just the sniffer obviously missed the asterisk packet. Okay. So there it is. We connect. Okay. Yeah, 23, 42. Okay. I thought that coming, so I saved another capture. So I export it here. I'll launch up BTCrack. I'll import the capture, which is here. We have everything except the BD address of the master and the slave. Now what is important is that we can get it with a sniff. It's just that Frontline choose to not display it for whatever reason. So there's a nice kernel module which happens to be known as BP105, which actually shows both. For convenience reasons, I just save them so I can copy paste them here. So we'll paste them here and here. So, okay, there it is. So there it is. The pin is 1, 2, 3, 4, 5, 6, and the link key is this one. So it's actually not the link, the pin you gave me. I had to load a backup file because I couldn't get the pairing to work over here. But that's basically it. It's a low-powered Centrino here, so it does only 44,000 keys a second. But you will see the problem. You get this key within 5 seconds. So now we can actually use that link key and connect to the master, pretending to be the slave, or pretend to be the master and connect to the slave, and we will be fully authenticated and have access to all services this device offers. Thanks. Okay. Yep, there it is. So what can you do with link keys? You authenticate to both devices, as I said. You can dump them from any Linux, Mac, or Windows machine. You can create an encrypted DELFs channel. That's pretty awesome. You plant the link key, and you can connect to the device without that user notice, because the pairing process, we go around the pairing process as we have the link key, and you have a remote shell or a remote OBEX server, whatever you choose, over an encrypted channel without actually planting a binary or something else. You just planted the link key. So that's really tough to find, actually. How to reinforce pairing, actually checked and rule proposed to inject LMP not accepted. Or before the master sends the random number, you inject in round, which is normally used when you don't have the key, so it falls back. Before the master sends the random, you inject an SRES message, which basically means the same. It will say, oh, he wants to pair with me. It doesn't have the link key, so I'll fall back. We propose to use BD address, which comes with blues, which is there as source code. You have just to compile it, and you can change your MAC address, your BD address. BD address, not BT address. BD address of your device. Connect to the master with an unknown link key, and it will say, oh, what? There's that device with an unknown link key. Well, I corrupt my pairing, I'll restart, and it will reinitiate the pairing process. So we now have a quick and reliable way to get the BD address, a way to crack the pin and the keys. What's left, that's the sniffer. So as an assignment, go and make one for everybody. That would really help out research, and there will be lots of bugs still to find. Things to remember, Bluetooth might be a risk for your company. Don't accept every file being sent. Well, that's pretty obvious. Disable Bluetooth if not required should be obvious too. Pair in secure places. That's a ZIC recommendation. It's your definition to tell what is a secure place in wireless. Don't use unique keys. Actually, you as a user can't choose. It's the vendor. Hold your Bluetooth vendor accountable for vulnerabilities. Delete your pairings because pairings are pretty much a backdoor to your device. And if possible, use Bluetooth specification 2.0 and simple pairing, which has elliptic key cryptography, which is very strong and should pretty much, well, let's say I don't know if it's really that secure. We'll see. I'm not a cryptograph, actually. So let's see how this works out. That would be it.